Thank you for coming to my talk. I'm going to start out with just a few examples of what I mean by data matching. Hopefully these are not new to you. The first one is data integration, and what I mean by this is you're trying to build one source of data from multiple other sources, and you want it to be cleaner and more timely and more correct, and you have links back to the original data so that you can get to it if you need to. Second application is what I'm calling enrichment, and the idea here is that you have some data set already built. You get data from a client. You match that client data to your own data and then pass them back some bit of information that they didn't already have, maybe an identifier that they need. The third one, which is pretty common in many industries, is what I'm just going to call record linkage. And the basic idea here is that you want to match records together, not so much because of the identities of the records, but because of the data that you have associated with them. This happens a lot in like medical research and the financial world. I'm going to use this concept throughout of what's called pairwise matching. And the basic idea is that you have two sets of data. Theoretically, you want to look at every conceivable pair of records in both data sets. There's one subset of that cross product that matches one subset, which are the non-matches. In practice, you don't look at all the data. You figure out some way to index it or pre-cluster it or whatever. This isn't actually the software architecture that you would necessarily use either. In most cases, you'll have some pre-established database and you read in data, try to match it to that. But I'm going to use this concept. The alternative way of looking at matching is the clustering approach, where you start off with a set of data or a combined set of data, and you try to build clusters from that, which is especially appropriate for de-duplication. But in practice, the computational complexity and the actual detail work that you have to do is very similar in each case. The test data that I'm going to use is from a blog post from a few months ago by the guys at Enigma. And what they did was they took a data set from the health department in Florida where they were inspecting restaurants, and they took a data set from the Department of Labor on wage violations. And they connected those together to see if there was a correlation between a company failing to pay their employees correctly and health violations in those restaurants. The short answer is yes, there is a correlation between those things. So the first step I'm going to run through is what I'm going to call profiling. Profiling is a huge set of things which covers a lot of stuff that I won't do here. But what I'm really looking for is keys in data sets that I can use to connect them up. We want to see if they're accurate, if there are enough of them to use for matching. Are they in a consistent format? And in some cases, are they recent? I might have several records for the same data. Some of them may be really old. I'm going to use pandas for all of this. If I suspect a lot of you are already familiar with it. Pandas has a command on the data frame called info, and obviously this is a little more info than you would want. And this is all the columns in the health inspection data. What you're really looking for is things that you might use as identifiers, and also the information on the right-hand side tells you, which of those are non-null. So to sort of pare this down a little bit, you can choose the things that you think are probably identifiers, drop the identical duplicates, and make a new data frame. And that's all I've done here for this for the restaurant data. So the stuff on the right-hand side tells you how many non-nulls you have there. So if those were 90% null, then that would probably not be a good field for matching on. And this is similar data for the similar command for the wage data. Some more interesting things you can do. A lot of times you have numeric fields in your data, and you want to see if they follow some pattern. So the case I've used is zip codes. Both data sources have zip codes. So all I'm doing is reducing the zip code field to a specific pattern, then grouping on that pattern and looking at the counts. So you can see in the restaurant data, they have both 5 and 9-digit zips, which they've put into 2 different forms. And in the second one, they have 5-digit zips, but since they're all numbers, Pandas by default interprets that as a floating point or as a int64, and the pattern comes up looking like a float, but it's a 5-digit zip. You can do slightly more sophisticated things. I didn't have a good example for this data set, but you can also use apply with regular expressions. This might be a good way to, for instance, check that email addresses are in the proper format or dates are in a particular format. All I did here was look at the leading pattern on the names just to see if I had mixed case. Another thing you can do with Pandas is it has a filter capability, which is kind of like group by having in SQL. And so this is just looking for cases in the restaurant data where the name of the company and the address and the city are all the same, and looking at those and identifying ones where those occur more than once, just to see if you still have duplicates in these data sources as they stand, which we do. Another thing you can potentially do is the series in Pandas has, yes?
How big is your data set?
These are, once you boil them down to just the location data, just the identifier data, one set is about 54,000 rows and the other is 17,000 rows, I think. So, pretty small. And in general, Pandas is going to work on things that fit in memory, but now that you can get a 2 terabyte instance on Amazon, lots of stuff fits in memory. So the series has a thing called value counts, which just gives you a list of the most common things. The example I used here was the DOL data has both a trade name and a legal name, and it's not immediately clear to me, at least, which one of those you might want to use as the name. So if you look at the value counts on legal name, those don't look recognizable to me. But if you look at the counts on trade name, those look like businesses to me. Also, Pandas you can make nice graphs with, and this is a case where these name strings I want to compare. A lot of times when you're doing matching things, you'll find that in the original data source, the person who built the data said, this is going to be the name field, but I'm only going to dedicate 20 characters to it. And so what happens is that half the words in the name are abbreviations. And so if this might be a useful way to determine that your names aren't really closely comparable, which it seems like they probably are here. So the next step, the thing we have to figure out is how to compare these records next. What we really want is a function that will take any record pair and tell us, yes, this is a match, or no, this is not a match. We could, of course, do that if we restricted ourselves to identical matches. But in practice, what happens is you compare the fields in each record, usually using some sort of similarity function. Sometimes it's identical comparison, but it's usually some sort of distance metric, a string similarity function or other distance metrics. And what you end up with is what is usually called a comparison vector. And then from those comparison vectors, you make decisions about what is and isn't a match. The first thing you typically have to do to your data before you do these comparisons is some sort of pre-processing. And I'm not going to spend a lot of time on this because I think you've probably all done it or seen it in some form or another. But it's usually things like standardizing on a particular case and removing abbreviations, standardizing on a zip format, parsing things or sometimes it's called segmenting things into pieces so that you can compare them more easily. And this is just it's the simple way I've done it on my test data with Pandas using apply and lowerizing fields and taking substrings. This is a trick I discovered recently with Pandas where I really like, where you can actually split the strings. So I just threw that in there because I think it's cool. So probably the most well-developed area of similarity comparison is in string comparisons, and there's a bunch of string similarity metrics or functions. And these are just some that you have available to you in Python. The ones that are highlighted there are the ones that I'm going to look at in more detail. The jellyfish library in particular is very useful for, to me at least, for data matching. So Levenstein or edit distance, you've probably all seen it in some context before. It's kind of a basic computer science thing. Basically, the edit distance is the number of one-character edits you have to make to get from one string to another. And I've just transformed PyData into pandas by making one-character edits in this slide. The next two I'm going to talk about are called the Yarrow and the Yarrow-Winkler one. And I'm going to show these in a little more detail just because I don't think they're well known. They're not used a lot in other machine learning or statistics applications, but they're used a lot in data matching and record linkage. These both came out of the Census Bureau, I believe. That's the basic form of the Yarrow similarity metric, and then the Yarrow-Winkler variation of that just takes the same thing but puts more emphasis on the initial part of the string. Especially when you're looking at businesses, that turns out to be very useful. Another one that comes up a lot in a lot of contexts, even in clustering and machine learning, is Jacquard similarity, which, again, you're probably familiar with. It's just the ratio of the intersection of the sets to the union of the sets. The nice thing about this particular method is that you can use it on strings, you can use it on tokens, and quite often you use it on n-grams, or what are called shingles in some applications, which is what I've done there on the bottom. So that just means you're taking overlapping subsets of the string and comparing them. So what I'm trying to show here is how effective these things are. This presumes I've already done the matching, and so this is on the data after I've done the matching on the test data. The graph on the left shows the scores for the matches for each metric. And you can see that the Yarrow-Winkler one gives you pretty good scores on the matches. And then on the right-hand side are the scores on the top, I think it's the top 1,000 non-matches. And so what I'm trying to convey here is that the Yarrow-Winkler metric gives you really good separation. So it gives you relatively lower scores on the non-matches and relatively higher scores on the matches. Again, that won't be true on every data set, but in data matching applications, especially with businesses and sometimes human names, that's often the case. There's again, a bunch more sophisticated versions of these. One that I would particularly recommend looking at if you're interested in this is what's called soft TF-IDF, which is just an extension of term frequency, inverse document frequency approach, but using it in conjunction with other similarity metrics. It's actually probably the best one that I know of, the best similarity metric that I know of, but it's considerably more work than the others. Human names. Human names are among the more tricky things to match. I don't have any human names in my test data, so I took some examples from some financial advisor data. This is actual data taken from actual Department of Labor and other data sources. And these are all do refer to the same guy. You can see some of the common things. People make mistakes. There's OCR errors. They concatenate things together. And then the kicker is if you Google for this guy, he actually goes by Rick, which again is a tricky thing with human names. So just some advice on human names. If they come in your data source, if they come as a single string, you almost always want to parse them out. It's easier to compare things that way. Based on my own experience, don't try to use a regex to do that because you will go insane. If you're trying to be really precise, substituting first names is a useful thing to do. One warning there is that there are databases of first name alternatives on the internet. I would not start with those. Sometimes they'll have 200 alternatives for a first name, and that will just blow things up for you. If you're doing this as part of a data product or an ongoing process, a lot of times you just have to make a dictionary of matches that you found previously and do lookups. And then finally, sometimes it might be more, you might have data that has a name and also the employer. It might be more useful to figure out exactly who the employer is first and then use that as a data point to match against the names. There's a good Python library for doing name parsing, which does a pretty good job in a lot of cases. It's called Name Parser. People have also packaged this into an online service. As you can see here, it does a pretty good job on a pretty sophisticated long name with titles and prefixes and so forth. However, it is purely syntax based. So if you have a case like this where it's last name first, if you don't have the comma in there, it's not going to know that Richard is a more common name. It's just going to assume that the guy's first name is Breger. Addresses. Addresses are even potentially trickier. The only good thing about addresses is there's this huge body of work having been done on geographical information systems over the years. I think I'll just skip ahead to the geocoding stuff. But one note of warning is just because something has the same address doesn't mean it's the same business. I call this the food court effect, which you can sort of see here. There's also an interesting little catch there. There's an incorrect zip code in this data. So geocoders are basically tools that take an address and give you back latitude and longitude and other information potentially, and they also parse the address. There's a bunch of them. Google's is probably the best, but it's not free. Most of these services are not free. There is a geocoder called Tiger, which is an add-on to the PostGIS extension to Postgres. And it works pretty well, but you have to set it up yourself, and you have to get the data from the Census Bureau. I've shown here an example of how you invoke Tiger from pSQL. And you can see you give an address, and it gives you various bits of information about that address. The trick with geocoders is that they're only as good as what you give them in input. So you can see there in this table, there's a rating value. And most geocoders will return some sort of rating that says, yeah, I know where this is. You can trust this latitude and longitude. But if you give it a incorrect address and it can't find that, it will give you a rating that says, this may not be where you think it is. And if it gives you a really high rating, it's probably saying, I don't have enough information to determine this precisely. So in the last case, I'm just giving it the name of a city. So it's probably giving something like the center of the area bounded by that zip code. Just quickly, to actually compare the distance between two places, you have to do what's called the Great Circle distance. In practice, you don't really need to do that for matching because you don't really care exactly how far apart they are, just are they close. Let's see here. There's been a lot of work on segmenting addresses and names using sophisticated techniques like hidden Markov models and conditional random fields. That's again a talk in and of itself, so I didn't want to go into that in detail. I mentioned earlier that in this pairwise matching approach, you conceptually looking at every possible pair. In practice, you can't always do that. Even in our relatively small data sets here, we've got around 800 or 900 million record pairs. So you do this process of blocking, which means doing some sort of pre-clustering to eliminate all of the obvious non-matches. Sort of a conventional way to do that, which doesn't work that well in a lot of cases, is to generate what's called a soundex code for the name. You can see here I've generated soundex codes for all of the names in both sources, and there's at least one there where it matches up. So if you were to use the soundex as the blocking code, you'd only have to match within this set instead of each name across each set. Sometimes you can just use the key properties. For instance, if you use the zip code, this isn't the whole data set, but that red band there is essentially the ones you would have to match if you just use things where the zip code was the same. Now everything that's in blue you can throw away. The problem with that obviously is that you miss matches because there's going to be some actual matches that don't have the same zip code. So a lot of times you use more than one of the keys. You use the zip and maybe the street number and something else. Also, one detail is you may have to do that sequentially rather than making one big set of data to match. You may have to get the statistics right in some of the later techniques, you may have to do that in stages. Another thing that works pretty well on messier name data is what are called n-gram-based blocks. And the basic idea here again is you take n-grams. In my case, I have bigrams. You take the bigrams of the string, and then you take some subset of those and put them into a chunk, and that serves as basically a key and an inverted index. I made this picture hoping that it would be a little bit clearer what's happening. The things on the left are basically the index elements, so they're sets of bigrams that have been put together into length of a 16-character string, and those two names there. They are in fact the same place, and you can see that they share that top key there. Again, this is a really big field. There's 1,000 different ways to do this. Canopy clustering is used. I have not personally used this myself, and my understanding is it's kind of difficult to get the thresholds right to make this work. But it's sort of like a pre-clustering approach. Locality-sensitive hash, in particular min-hash. If you don't know min-hash, look it up. It's one of my favorite ideas in computer science and can be used to do this blocking operation. And there's been there's a gentleman in the audience who did a really good density-based clustering talk yesterday, where he did a deduping example, and so there's a lot of clustering approaches that can be used for blocking as well. Okay, now the last step is we've made these comparison vectors, and we have to figure out, are these things a match or not. The four things I'm going to hopefully talk about are simple scoring, rules-based, probabilistic matching, and just supervised learning. Mostly on the probabilistic matching stuff, because that's the most interesting, I think. Simple scoring means you have this vector of similarity metrics. You add them up. You say anything above a certain threshold is a match. Anything below is not a match. That actually works reasonably well on our data set. What this shows is the blue is the matches, and the red is the top non-matches. So you can see it does separate them somewhat, but there is this area of overlap between like 2.7 and 2.9 where there's both non-matches and matches. And the real issue with this is not so much that there's this overlap, but the problem with it is it doesn't really tell you anything about where the boundary should be. Another really common approach is using rules, and there are ways to learn rules from the data, but a lot of times these are just made from people who know something about the data to begin with. The main benefit of this over just basic simple scoring is that you can use multiple rules for different situations. So you can say, if the similarity in the name is over 0.8 and the zip code is the same, I'm going to assume that's a match. But you could also say, if the similarity is over 9.5, I'm going to regard it as a match, irrespective of what the zip code is. So and these get relatively complicated. So there's this idea of probabilistic matching, which has actually been around since, I think, the 1960s. And these two gentlemen, Filegi and Sunter, did a paper in the 60s, I believe, that detailed this idea. So in this case, our comparison vector is basically a set of predicates. So what I've used here is the first predicate is the name is over a certain threshold, the zip is equal, and the Levenstein distance between the street numbers is less than 2. And given that comparison vector, there's 8 possible patterns that you could see. I've just delineated them there in this little data frame table. The basic idea is that certain of those patterns are much more common in the match set of matches, and some of them are much more common in the set of non-matches. And so they define these two conditional probabilities, M and U. M is the probability that you see that match in the match set. U is the probability you see that pattern in the non-match set. And then using that data, you make what they call a linkage rule, which again is just the thresholds that you pick to determine what's a match, what's a non-match, and what needs to be reviewed. And sort of their insight was that they showed that these ratios can be used to define, given the data that you have, these ratios can be used to find essentially the optimal linkage rule given the level of error that you're willing to accept. So, you know, if you say I'm willing to accept 1 out of 1,000 incorrect matches, then you can adjust these thresholds given the M over U ratios to get the optimal set for that level of error. So there's two simplifications that are almost always made to this approach. One is to assume conditional independence between the properties. And then the other one, which is probably not as important these days, is you take the logs of the ratios to make a score. That just means you don't have to multiply the individual conditional probabilities together. You can just sum them. So you've probably noticed that this method sort of depends on actually knowing what's in the M set and what's in the U set to begin with, which would kind of defeat the purpose if we already knew that. There are some ways to do that just involve knowing something about the data and progressively refining it. But the technique that people have arrived at over the years to do this in a more precise way is the expectation maximization algorithm, or EM algorithm. The basic idea here is that the distribution of patterns in our data set is a mixture of some parameters. In this case, it's the M parameters, the U parameters, and some extra parameter called P, which is actually the probability of a match being in the set. It's also called the mixing parameter. So if you've used like Gaussian mixture models in scikit-learn, I think it uses the EM approach, and this P parameter is called the mixing parameter. Then the method then next assumes that there's this latent hidden variable that determines which set it's in. And then once you have that, you just have to basically find the parameters that maximize the likelihood function, which is, you know, pretty simple. That was supposed to be funny, in case. This is actually fairly easy to do, though. It looks a little nasty, but normally you take the log of this and use log likelihood, and it actually is pretty easy to program. If you look up the papers where they develop this method, the calculations you need to do this are not particularly onerous. So I can't actually run it here. It takes a few minutes to run, but this is basically the sort of data that you end up with. In this particular case, we end up with a pretty large set of possible matches, which is unfortunate. But you can pretty much assume that anything where you have the 1-1-1 pattern, you can probably assume those are good matches. According to the EM algorithm, those are only about 1 in 10 billion, roughly. But the rest of them might require some sort of clerical review, and there are sort of ways to optimize this. But I've always worked in situations where I had a data team available to do the clerical review on the near matches, and if there's 10,000 of them, that's something that a team can get through pretty quickly. Or you can use something like Crowdflower. So you can use normal supervised learning classification approaches on this stuff. The trick is that you need labeled data, but that's not as unusual as you'd imagine, because you can often start with a set of data and use that to train, and then just use here I've used like the scikit-learn random forest classifier. There is one trick with this, which is that it's hugely unbalanced. So even if you've indexed the set and reduced the number of things that you want to match, in this particular case, I found about 1,300 matches, and the reduced set is well over 1 million of the comparisons I had to make. And the other problem is that the distribution of things in the non-match set is not very even. And so there's two things you can do, which is one is you can try to restrict yourself to just using non-matches that are close, which has certain problems. Or you can, there's probably not an optimal way to do it. You kind of have to get a set of data which has things that what you want to distinguish between is the things that are matches and close non-matches. But what happens is you end up, in this particular situation, even though it's about 94% accurate in this cross-validation, if you look at the feature importances down there at the bottom, basically all it's doing here is optimizing the string similarity distance. This graph requires a little bit of explanation, but what I was trying to convey here is that on the y-axis is the simple scores that we used several slides ago, and you can see there's not a big range of those. So just eyeballing it, you probably wouldn't separate those two things, but the random forest classifier does a pretty good job. The things on the right are the thing in red are the thing that are matches, and so the x-axis is the probability of it being a match according to the classifier. So it does a pretty decent job of figuring out which isn't a match. A final few things to look into if this interests you. One is, and the probabilistic matching, you can make a lot of modifications to that, and one is that you can take into account the fact that certain patterns in the data are less likely. So if you're doing, say, a name match, if you find a match between two guys named Smith, that's a less interesting match than many other names. There's a couple of tools now which use an approach called active learning, which is basically what you start out with a training set, and it separates the fairly obvious different things from each other, and then it goes through a process of saying, I don't know about this one. Is this a match or a non-match? And so you run through. It'll prompt you with several examples, and after you've run through maybe 100 of those, it'll be trained to recognize those things that are kind of near matches. There's a product called de-dupe that's hosted by Datamate, I think, that does this. It's a pretty cool tool. It was based on a gentleman's master's thesis, so there's also a pretty detailed paper on it. And then there's a program called Febril. I'm assuming that's how it's pronounced. It's a Python program that is used for record linkage. It was written, it's from Australia, and it was used for biomedical record linkage. It has some of the Fliggy Sunter stuff in it, so it's another good resource to look at. Oh yeah, the gentleman who's primarily responsible for that package also wrote what's probably the best book on data matching, which is descriptively called Data Matching. I think his name is Peter Christensen. Kristen, okay. Yeah, good book, I recommend it. I think that's all I have.
I've got a question, right? Let's say you've got a more qualitative attribute, like state, you can geocode, right, and turn it into number. But let's say you have something like industry, where there's a lot of subjectivity involved in terms of trying to quantify that. Things like one-hot encoding, right, present themselves as a way to try to have an objective measure of distance if you want to throw that into k-means or something that doesn't always scale. So I guess what I'm asking you is, do you have any thoughts on how to scalably approach, scoring or distancing on qualitative attributes?
Well, industry in particular, there are industry identifiers that have a sort of distance to them, like NAICS codes and GICS codes and things like that. They have sort of a hierarchy, so they're like zip codes where the initial part of the code describes the industry broadly, and as you get into more detail, it gets more specific about the industry. But I'd have to think. I don't have a good answer for you on.
Even with NAICS, right? Yeah, once you're into a given sector, it gets a little more specific. But that top, the first number, if something starts with 2, it might not be that far from 7 or whatever.
Yeah, yeah, I know what you mean. I just don't have a good answer for it.
So the definition of zero distance and 1 count per tau is number of transposition.
Yeah. So a transposition in particular is just 2 letters that are switched. So if you have 2 strings and you take one of them and you switch the 2 letters, that would be 1 transposition difference between the 2. Does that help?
So that have to be consecutively.
Yeah, they have to be consecutive. Yeah. The reason why that's in there in particular is a lot of these edit distance metrics were specifically built to address the fact that this data was entered primarily by humans, and sometimes by hand and sometimes with computers. But a human is most likely to make a 1-digit or 1-letter transposition.
You mentioned shingles earlier in your discussion. Can you tell us what they are and what they use?
Sure. So it's basically an alternative term for n-gram, so which can be applied to both sequences of characters and sequences of tokens. So they call them shingles because they overlap, like the shingles on a roof. So if you were looking at bigrams, for instance, you take the first 2 characters of the word, and that's the first bigram, and you take the second and third character of the word, that's the second bigram. Those are also called shingles, and they can be of arbitrary length as long as it's less than the length of the actual string or sequence.
And what are you using them for?
They're basically, they give you a little bit of more structure to the data. So if you're with Jacquard distance in particular, since it's just a set-based thing, you can have 2 words that in terms of Jacquard similarity would be identical because they have the same characters, but they would clearly not be the same word. But if you use bigrams or shingles, then you're giving some structure to that sequence, and so the 2 things that are the same set of characters but don't have the same sequence would score lower using the shingles. Again, this is an idea that comes up in MinHash, the locality sensitive hashing thing. So there's a paper from the 90s by Andre Broder, which is really cool on this idea.
So come back to that zero distance or zero similarity. So given that definition, why the coefficient of the tau is negative? Should it be positive to capture the similarity?
Why is it what?
So my question, why the coefficient in front of tau is negative?
Oh, I think it's subtracting the number of transpositions from the number of common characters.
Right. So
Yeah.
should it be positive?
I'm pretty sure it's supposed to be a subtraction, but I can't explain necessarily why.
The more transpositions, the lower similarity.
True, yeah.
But the intuition is the human input will impossibly make the same address of transposition. That means you want to add that similarity.
Well, I think I think what it's trying to capture is that people sometimes make the transposition error, Yeah, I see what you're saying. Yeah. Yeah, I can't answer your question. Thank you.